How's everyone doing? Didn't hear from everyone. How's everyone doing? All right. Okay. Today should be fairly quick, sort of, but it should be very understandable because we're going to be talking about how you can see the derivative in a graph. Now, the good news is we have graphing calculators, we have Desmos, so we can actually see it. Again, I refer back to when I was taking this class in the 1980s, early 80s, we didn't have those kind of things. We had a little one-line calculator that cost like $300. And so we had to use all these techniques to actually figure out what the graph was going to look like. We're actually have the advantage that we can see what it looks like, but we're applying these calculus concepts from hundreds of years ago that were discovered when there wasn't technology. So we'll use both. We'll use the technology to take a look at the graph, see what it means, and then also think about this as the concepts are still important. Even though you can graph and see where even though you can graph it and see the graph itself, there might be instances when you're designing something where what you have is data. You don't really have a function. And that data itself can help you look about rates and derivatives. And if you understand the concept, that's going to help you in the long run as well. So I just wanted to go back and as we start in, remind you that we have the mastery test next week at this time on Wednesday. There are these resources here in the mastery test preparation resources. And again, these are not new resources. They have always been there, or not in Canvas, but they've been in the MAT265 page. One of the ones I think that you might find the most helpful if you're feeling pretty much on track is this this link here, the new mastery post. It actually gives you a derivative to take. It gives you multiple choice answers. You get 4 of them. 1 of them is correct. 3 of them are wrong. That's how the test is. It's just a bunch of functions, take their derivative, and choose the right derivative. So it'll give you preparation that way. There's also a paper version, and then if you still are struggling with some things like maybe the chain rule or power rule or something, there's the math shower, which has broad resources over all derivatives. Okay, so that's a good place to go. But for now, we're going to focus on 4.3, which is looking at derivatives and graphs, or if I got the function graph, what will the derivative graph look like? And what does the derivative tell us? So there's going to be some derivative tests. We're going to use both the first derivative and the second derivative to find various portions of a graph. Just a reminder, so we're here on this Wednesday. There's the overview. We'll have our mastery test next Wednesday, and then I'm going to be out of town on Friday, so I'm going to post a video review of, I'll be here this Friday, but next Friday I'll be in Cleveland. Anyone from Cleveland? Any advice? I've never been to Cleveland. I don't know. Anyway, so that Friday you can watch a review video over 4.1 to 4.4. And then we'll just kind of continue on. We have some sort of holiday. What's that? Oh, that's Veterans Day. And then we've got a couple more sections, a review, and then exam 3. Okay. Let's see what's going on. Oh. So first of all, the features of a graph of a function that we're going to be interested in or have tools to find is we'll be able to use one of the derivatives, actually the first derivative, tell whether a function's increasing or decreasing. Okay, we've probably already thought about that, but we're going to formalize that a little bit. We'll also be able to find maximum or minimum. So far we knew that if the first derivative is 0, we've got a maximum or minimum, but we don't know which one. So we're going to look at what's happening and use some further derivative testing so that we can actually say, okay, we know it's a maximum or minimum, but now we'll be able to tell you which one it is. Concave up, which is we would just say holds water, so like a glass, or whether it's concave down. So that has to do with the rate of change, whether it's increasing at an increasing rate or increasing at a decreasing rate. That can get us confused, or is it decreasing at a decreasing rate? So it's the rate of change. And so when you see that, a rate of a rate, you should start thinking second derivative, because that's where the second derivative is. It's the rate of the rate. Okay? And we've got some tests that will tell us that. And again, so we know what's happening. All these are helping us to get to maybe some sort of future prediction. Or again, if we're designing something, maybe it helps us get it more efficient. And then we're going to look at something called inflection points, where it changes from concave down to concave up, or the other way around, so concavity changes. So those are the four things we'll look at. Oh, I forgot to do this. So first of all, for increasing, decreasing, I kind of got the rule down here. Does it make sense that if the derivative, the slope is greater than 0, if it's positive, it's increasing? I mean, we've done this with linear functions. If the slope is positive, it's increasing. If the slope is negative, it's decreasing. The slope is the derivative. That's what we've been talking about. So to talk about increasing, though, or decreasing, what we mean is as x increases. X is always increasing because we have to read from left to right. And I highlight that because I don't always read from left to right. I don't know if I told you the story. I took Arabic my sophomore year simply because Arabic is written the other direction, and I can write with my left hand in Arabic, or used to 30 years ago I could. But that's what I liked about it. It was that kind of thing, because oftentimes I would read in both directions. And that's what gave me problems with graphs, is I would tend to read a graph both ways, and so I would see something that should be decreasing, but I would read it backwards, it looks like it's increasing, right? So when you read a graph, we have to force ourselves to go left to right. So x is always increasing, but then we report whether y is increasing or decreasing, okay? So increasing is as x gets larger, y is getting larger. Decreasing as x gets larger, always, y is getting smaller. Okay, so that's my definition of it. And then from linear functions, we see what increasing means is as we go from left to right, the y's are going uphill. So a positive slope, a positive derivative. And we'll talk about it in terms of other, not just linear functions. And then decreasing, going downhill from left to right. So the slope is negative, the first derivative is negative. Okay, so we take a derivative and find its sign, we know whether we're increasing or decreasing at that point. Okay. So here's an example. They call this the I/D test, increasing, decreasing test. It took me a few minutes to figure that one out. But so what do we need to do? We want to find where is this function increasing, where is it decreasing? So what would you suggest to do first? Find the derivative. Good. So we'll do that. Because, oops, I didn't want to show it yet. Okay, so we'll take its derivative. 4 times 3 gives us 12, x to the third power. 3 times 4 is 12, x to the second power. 2 times 12 is 24, x, and the derivative of 5 is 0. Okay, so we've got the derivative now. Before we look at the graph, how can we find where it's positive or negative? What might be sort of a first step to look for? What? Inflection points is coming next, but you're kind of right. We're looking for critical points where the derivative is 0. Because if we find that, then on one side, generally on one side it'll be positive, one side it'll be negative. There's a couple instances where it might be. So critical points. And so we set the derivative equal to 0. Before I write it out, what I'm going to do is I'm going to factor. I can factor out a 12, and I can factor out an x. So I get 12x this becomes x squared, this becomes x, and this becomes 2. So we can keep factoring. We got 12x, x squared minus x minus 2, I think should factor into x minus 2, x plus 1. And so we can solve for our critical points. We're going to get one. This one gives us x equals 0. This one gives us x equals 2. And this one gives us x equals -1. So those are our critical points. Those are the place where the derivatives are 0. Then what we could do is we could look at these critical points, these x values. So we could start, say, with x equals 0, and we could look to the left or the right, slightly to the left, maybe at 0.5, okay, and see whether -0.5 and 0.5, see whether it's positive or negative. And do that for each of them. So we got to look at 6 points, right? Does that sound kind of tedious? Plugging in a lot of points. So why don't we graph it and take a shortcut? Because technology can give it to us. We can look at it on a table of values. So this is the original function. And what we found, the critical points from the last stuff we were doing, what we found is that here's the -1, here's the 0. We found minimum values. I think my recording is not going to get everything, but that's okay. Okay, so we get these minimum values, or minimums or maximums. We know that those are the places, I mean, that's what it looks like where we should have the derivative equal to 0. So -1, 0, and then x equals 2. And we could kind of see here that this is decreasing and then increasing, right? Decreasing here, and then on this side it's increasing. What we could also do at this point is we could graph the derivative itself. And remember, in Desmos you just put like d dx of the function, or you could find it and graph it. And so I've overlaid that on top, and here's another way. So we do see down here the derivative is negative. All that area is negative where it's decreasing. Now it looks like the derivative is increasing, which it is, but remember that's when the derivative is below the x-axis, that means it's 0, it's negative, which means the original function is decreasing. So this is the practice you kind of want to get to, is that when you look at the derivative, it's like looking in the mirror and trying to cut your own hair, which I do. So, and it's hard to do sometimes, because everything's kind of backwards, and so your instincts are a little bit off until you train yourself to do it. I don't know if there's this one video goes around. Somebody made this bike that when you turn it this way, it goes that way, and when you turn it this way, it goes that way. Have you seen that one? They played a lot for teachers and such, because you have to relearn how to turn. You think it would be easy, but it's not. And the guy who made that, he taught himself how to ride it really nicely. He couldn't ride a regular bike after that. So anyway, that's the thing, is that the derivative is sort of operating differently than the original function, but so what we're looking for is a sign. And then this whole part up here, see, that's all positive derivative, right? Because it's above the x-axis. And so then you see in the red graph, which is the original graph, that's increasing. So we can actually just graph the derivative function, and it's going to tell us where the function itself is increasing, decreasing. Okay, but that's kind of the technique to go through, and so we can see what we do is, okay, now from this interval, where is it, let's talk, the type of question you'll get is what are the intervals where it's increasing or decreasing? Decreasing. And we could either tell from the first derivative test or from the graph itself that from -infinity until, well actually till -1, -infinity to -1, and then at unions we've got a break. We can see it's increasing here, but from 0 all the way to 2, the derivative is negative. So sometimes it's a little easier to see that 0 to 2, the derivative is negative, so we're going to have decreasing, and then that's it, because then the derivative from that point on, from 2 on, is always positive. So we could then also list the increasing intervals simply by looking at the derivative. Again, we could also look at the original function, but we're going to see it's going to be increasing from -1 to 0, and then from 2 to infinity. Okay, so that's how we could use the first derivative to help us maybe be a little bit more sure of what's happening. And it helps us find the zeros. And so those critical points can, again, they are going to tell us where we've got a maximum or a minimum. And doesn't it make sense, if we've got a maximum, half of it is increasing, the other half is decreasing, right? It's like you walk up a mountain, you go down the other side, you have to work to get up it, and then you can slide down. If you've got a minimum, you're down at the bottom of a valley, you decrease and then increase. Okay? We're going to take advantage of that.
I found this on the web.
We're going to take advantage of that part of the derivative as well, and be able to now not just use the first derivative to say where a minimum or maximum is, but to say whether we have a minimum or a maximum. Okay, we could do this all with the first derivative. So the minimum test is kind of what we just did. You go through, you find the critical points, you look on the left or you look to the right, and if there is a change of sign of the first derivative, right, from positive to negative or negative to positive, that's going to tell us we've got a maximum or a minimum. So if we go from positive to negative, that means we went, remember, positive derivative means above the x-axis, it means we went up the hill because we had an increase. And then a negative derivative means we're coming down the hill on the other side. So that's got to be a maximum. Okay. It's kind of like, I guess, like riding a roller coaster with the blindfolds on. You could figure out what's going on simply by the feel. And that's really what a derivative, that's what a derivative feels like. I mean, your homework is go ride a roller coaster and you'll feel the derivatives. In fact, you'll feel acceleration, right? You'll feel the speed. You'll feel it all. Okay, so we've got a local maximum whenever we go from positive to negative of the first derivative. So increasing to decreasing. Does that make sense? Intuitive? Yeah. It's like you would see. I mean, you could see it. And then conversely, if we go from negative to positive, means we decreased and then increased. We went down into the valley and we came out. Okay, that's all it's saying. But we could do that with the first derivative. We could also graph the original and see it. Got it. But we can do it with the derivative as well. And again, sometimes we're in a situation where we have a bunch of data it's not really a function that we can play with yet, but we can look at what's happening to that data and see the changes in the data and maybe pull the derivative off of that. They do that a lot in the business calc because in business you've got all sorts of sales figures and stuff, and you're wanting to know, are we increasing or decreasing? Are we going to make a profit this year? Is things going to turn around? All that kind of stuff. But there's one third thing that could happen is that we don't get a change at all. So that we're maybe either have negative on both sides or positive on both sides, and we're going to see that might lead to an inflection point, but it's definitely not a maximum or a minimum, because you can't increase and then increase and get a maximum, right? You can't decrease and decrease some more and get a minimum. Okay? It's just, yeah. The only way you get a minimum is you have to go back, you go down and up. The only way to get a maximum is you go up, but you got to stop going up so that becomes a maximum point. Okay? So there is a possibility that just because we've got a critical point equal to 0, right, doesn't mean it's a local maximum or local minimum. But oftentimes it is. Okay? We got to look to both sides. And again, we can go through the tedious step of finding the critical points and then plugging in values to the left and the right and see whether they're positive or negative. But that's very tedious. We could also just graph it. My suggestion is to graph it and then look, is it above the x-axis or below the x-axis? It's a lot easier to see. Okay, so here's an idea of a local maximum, right? At the top, the derivative was 0. We found that critical point. If we look to the left, our derivative is positive, so we know we're increasing. On the right, the derivative is negative or decreasing. We know it's got to be a maximum, even without seeing the graph, just knowing this data. Okay. And again, there's situations where we have the data and we know, okay, we're derivative is positive here, is negative here. We can maybe assume that somewhere in between there's going to be a maximum. Sometimes we don't always know where that maximum is, but we know what's happening on both sides of an event. And so we know we're going to get a maximum somewhere. So this is the types of things it can help us with. And there's a picture of a minimum, right? Let's see if we can do it this way. Decreasing on the left, so it's got a negative derivative. The derivative on that side is negative. You plug in any of those values, you get a negative derivative. On the other side of the critical point, derivative is positive. Okay. Again, we can see it, but we can also analyze it analytically with just looking at the first derivative. And then what does it look like? There's two possibilities where it doesn't change, and you see we're increasing, we get a critical point in the middle, but then we increase on the other side. Or we're decreasing, get a critical point, and decrease some more. That's what we call an inflection point. And it's an important point too, but it's not a minimum or a maximum. So if we're looking for a minimum or max, this is a type of critical point that doesn't have it. Okay, we okay so far? And again, I like this lesson, this part of it, because we can always look at the original graph, and sometimes it's good to look at them separately and just see how that derivative graph is matching up with the actual original graph, and then try to figure out, they're going in different directions, but they're giving us different information. So here's an example. They gave us the same one to do. So we've already taken the derivative of this. We've already found its critical points. So let's see if I can get this right. I'll go ahead and take its derivative and factor it at the same time. What was it, x minus 1, x plus 2. We'll look back, and again, I didn't actually factor and take the derivative. I just memorized what the last line. So you would take its derivative, factor it to find critical points, just like we did, and we got that x equals 0 is one critical point. Well, or was it plus 1? Did I get that right? I did? No? I thought I got I always have to get something backwards, right? But the thing is I always realize, I'm probably going to get something backwards. And if I didn't, then double get. Okay, good. So, when I went here, I thought we had x was negative 1. So this, you solve for 0. So we get x equals negative 1 is another one. And then x equals positive 2 is another critical point. And again, we would look to the left or the right, and we could plug in points. So we did that to figure out whether we had maximums or minimums, and by figuring that out, we're also figuring out, or actually, at the last one we did it, we were just interested in whether we were increasing or decreasing, right? So we did that, but that same test really helps us know whether we have a minimum or maximum. So we're just taking that same data, using it to analyze it for a different purpose. First purpose, are we increasing or decreasing? That's it. This one, do we have a minimum or a maximum? And again, we can see that, let's go with orange, I don't use that much. At this point, negative 1, the derivative is negative to the left of negative 1, and the derivative is positive to the right. And so we've got negative to positive, we should have a minimum, and you see in the red graph, it sure looks like a minimum. And again, if you can see the graph, you say, why do I even have to use the derivative test? It's just preparing you. You know those guys who like throw knives with blindfolds on? They probably didn't train with blindfolds on, right? I hope not. They got good at throwing knives, and then they could put the blindfold on and still do good. This is it. We want to see the graph so we don't have the blindfolds on, because there might come a time, who knows, in your career where you're going to kind of have that blindfold. You're not going to be able to see the graph. You see the data or you see something else, so you'll be able to apply these concepts. Okay. And again, we could do that by plugging in and getting that, but we got the graph, we can see it now, we're good with it. Just take the activity of saying, okay, look at the derivative graph and say, okay, it's going from negative to positive, that's why I have this minimum. And then we see, and that happens all the way to here, so then at 0, I go from positive to negative, and we see at 0 what's happening. Positive and negative, that gives us a maximum. So we went up the hill and then we coming down the hill. And then the other place we had a critical point was at 2, and I see I go from negative to positive of the derivative, and so that it solidifies that I have a minimum when x equals 2 of the original graph, because I was decreasing and then increasing. Okay, does that make sense? All right. Try not to over-belabor it. But do take that advantage and the homework will do it. They'll give you a function and ask you to kind of do these. Go ahead and take the derivative, find the critical points, take a look at the graph as early as you'd like to, take a look at the original graph, and take a look at the derivative graph. And then go through the activity of comparing, the derivative graph is negative here, that means decreasing. The derivative graph is positive here, it means increasing. And if we, where the zeros are, you should be able to see it all on the graph, but go through and do that. Okay. So we got 2 out of 4 so far. Concavity. What is concavity? Well, those of us who wear glasses, we have, our lenses are all concave, so that's what allows them to work the way they do. So concavity. We have 2 types. Concave up, we say, could hold, so if it rained, it would be a puddle, it would hold water. Concave down isn't going to hold any water, it's going to spill. So that's the way to think of it. There is also a formal definition, is that concave up means that when you take all the tangent lines, the graph is above all the tangent lines. And we'll take a look at a picture of what that looks like. And concave down means all the tangent lines, the graph is below all the tangent lines. So this is concave up. So it's not necessarily always increasing, because what we'll see is that we could have concave up and part of it can be decreasing and part of it could be increasing. But it certainly, it will give us a minimum possibly. Okay. So that's a good example of it. But this is an example of a concave up. Here's an example of concave down that it's, so this is the function itself is still increasing, but it's slowing down. So it's increasing at a decreasing rate. It's deaccelerating, it's slowing down. Okay, and so that gives us a concave down. Okay, and again, for each of your fields of study, you'll have different applications for this, whether you're in electronics or mechanical or construction engineering or biological engineering, whatever type of, there's different applications depending upon what you're doing. But concavity becomes an important thing, because it tells us not just whether we're going increasing or decreasing, but it tells us the rate, what's happening to that. Okay. So there's really 2 tests, and I mentioned that it might involve the second derivative, and it's whether the second derivative is positive or negative. It will tell us whether it's concave up or down. And for this one, we don't actually have to find where the derivative is 0. We're going to do that when we get to the inflection point, because the inflection points where it changes. But I think I've got two sort of simple functions to work with. So if I take the first derivative of this, what do I get? I get 6x. And if I take the second derivative, what do I get? 6. Is 6 positive or negative? Is it always positive, or is it always? Yeah, it's always positive. And what does the graph of 3x squared look like? It looks like it's always concave up, which it is. So that's, so this is the idea. We've been using this. So what you can now step back in algebra, we just said, well, hey, if this leading coefficient is positive on a quadratic, we're going to have, it's going to open upwards. We didn't realize at that time probably that you were doing calculus or using the feats of calculus, because if you take two derivatives, all that matters is that leading coefficient, whether it's positive or negative, right? So if it's positive, it gives us concave up. If it's negative, what do you think it's going to give us? Concave down, because we take our derivative, we get negative 6x, and then the second derivative just gives us negative 6. That's always negative. And yes, just like you thought, it's going to give us a graph that's concave down. Okay. We'll look at this in terms of maybe larger functions where some parts are concave down, some are concave up, and there's going to be places where they change from concave down to concave up. That's what we call an inflection point. That's one of the definitions. So what do you think the value of an inflection point is going to be? How could we find an inflection point? What's 0? It's second derivative is 0. I'm not sure that we should call it a critical point. The book didn't even, I looked through it, it didn't even talk about this sort of second derivative test to find where it's 0. It just says find where the concavity changes. But if the concavity changes from positive to negative, what does it have to pass through? 0. You can't go from being positive to negative without passing through 0 unless you're not continuous, and we know how important being continuous is, right? So it has to be continuous. So we get to that. This is sort of a side point. We've already talked about max and mins, but because of what we just did with this concavity, do you think we could use a second derivative test to tell us whether we have a minimum or maximum? Certainly. We've done it already with algebra. We knew we had a minimum when we get a minimum when the leading coefficient is positive, right? So when the second derivative is positive, we've got a minimum because it's concave up. And when the second derivative is negative, that means it's concave down, so we're going to get a maximum. Okay. Now they do throw in this that we have to be at the point where the first derivative is equal to 0. Okay, so that's just a condition. Because why does the first derivative have to be 0? That's what makes it a minimum or maximum. If it's not 0, it's not a minimum or maximum. We could still be concave down or concave up, but it might not be a minimum or maximum. So there's examples of that where we're concave down, but we never really get to a maximum, unless but having the first derivative be 0 means that we're at a place where there's got to be either a maximum or minimum. Okay, and so we could use either the first or second derivative test for this. This is one of the ones that confused me. I go, well, we got the first derivative test. If that works, why do we have to have this? We don't. But if you want, it might be a little cleaner, but there's multiple uses for, again, it's a piece of data. We know it's concave up, and if we know we're at a place that should be a minimum or maximum, if it's concave up, it's going to be a minimum. If it's concave down, it's going to be a maximum. That's really all it says. So multiple ways to look at things. And now we're on to our last point. Our last thing which is inflection points. And we're just going to kind of tie everything together because what is an inflection point? It's a place where a graph changes from being concave up to concave down, or the other way around, where concavity changes. Okay. And again, they don't directly say it, but it's got to be also a place where that inflection point has to be a place where the second derivative is 0. because that's the only way it could go from being positive to negative or negative to positive. Okay. And so they give us some examples here. What does an inflection point look like? So we've got concave down here, and then we've got concave up on this side. So B is a place where those concavities change. And as we've looked at the other test on concavity, if the second derivative is negative, we've got concave down, which I think of as a frown. If its second derivative is positive, we've got concave up, which I think of as a smile, because positive things make you smile, negative things make you frown, however you want to remember that. And in between, it's got to be 0. That's where our inflection point is. Okay, so that's a way we can actually go about doing it. And again, this is concave up. This is kind of a funky function, but it's this part here would be concave down. So this point would also be another type. And then since this is concave down to concave up, D is going to be, you could get an inflection point that looks kind of like that. So there's multiple ways it could look. Now E is a sharp point. We can't take a derivative there, right? So we don't count that really as we don't count this one, even though it was concave up to concave down. Since we can't take the derivative, it's not differentiable, we don't count that sharp point as a inflection point. But P, again, is kind of a smooth one, concave up to concave down. So again, you'll kind of be able to see them, but to actually find where that point is, we now have a tool, the second derivative. If the second derivative is 0, from the graph we could see about where it should be. We could actually locate it exactly. Okay. So how do we find inflection points? Well, find where the second derivative is equal to 0, because that means where that happens, on one side it was probably positive, one it's negative. Find the sign of the second derivative on either side. And again, that's really the whole process we've been doing. Find where we've got a critical point where the derivative is equal to 0. Look to the left, look to the right, and see whether we've got positive or negatives. And if there is a sign change, then we've got an inflection point by definition. If there's not a sign change, we don't. We don't know what we got. Could be something else. So here's an example. So we've got a function. What should we do? We want to look for inflection points. What's your suggestion? Take the second derivative. But before we take the second derivative, what's yours? Okay. Why do you even ask, right? Okay, so we got to get the first derivative to get the second derivative. Of course, some of you might be sharp enough to directly get it. Let's see, this is 3 times 12, or 3 times 4, which is 12x squared. And then we want the second derivative. So this is going to be 12x squared minus 24x. Okay. And then we want to find where this second derivative is equal to 0. So we set it equal to 0. While we're setting it equal to 0, let's go ahead and factor it, because that's generally the way we do. I can see I can factor out an x and a 12. So I've got 12x out here. What's left inside is x minus 2. So I can see that I will get a place where the second derivative equals 0 when x equals 0, and another one when x equals positive 2. Okay. Then what I could do is I could look at the second derivative, right? Here's my, I could either look at it in factored form, or I could come up here and say this one. And let me just go ahead and do this. So let me take two, we'll just take one of the points. We'll take x equals 2. Actually, I want to be a little easy on myself today, so I'm going to take x equals 0. I'm going to look at -1 and +1, both to the left and the right. We're going to see what happens, okay? So the second derivative at -1, we plug that in, so we get 12 -1 squared minus 24 times -1. And again, what I did is I'm looking at x equals 0, but I'm looking what's happening to just the left of it. -1 squared is +1, so I get 12. Negative is positive, I get 24. I get a positive number. I could go ahead and figure out that that's probably like 36, but the cool part is I don't have to. I just need to know the sign of the number. I don't need to know what it is. So I know that my second derivative at this point is positive. So what does that tell me? Nothing quite yet. I also have to look to the right. So what does it need to be to the right in order for this to be an inflection point? It needs to be negative. It needs to be the opposite sign. So then I look at the second derivative at +1, which is to the right of it, and let's see what happens. I get 12 1 squared minus 24 times 1. So this gives me 12 minus 24, which is negative. And again, I don't actually have to do the arithmetic. I already spot it's going to be negative. So I went from positive to negative, so I know that at 0 I have an inflection point. Because I went from being concave up to concave down, right? Positive second derivative means concave up, negative derivative means second derivative means concave down. And then I could do this with 2 to figure out whether that's an inflection point. I think you'll see it is. The other thing I could do is I could just look at the graph, and it certainly looks like we've got inflection points at 0, and we have another one at 2, because we can see it going from the 2 was concave down to concave up. So with 2, the second derivative would have been negative to positive, which we kind of said, was, if it was negative at 1, which it was, then on the other side of 2, it's going to change to positive. So again, we really only needed to look at one more point because we had x equals 1 here. But again, the nice thing is we can graph these things, we can see them, but now we can actually pinpoint that inflection point. Because sometimes it's not always a nice even number, but we can say, okay, let me just take that second derivative, find where it's 0. And sometimes I can't factor it, but what I could do is I could graph that second derivative and just find its x-intercept. That's going to pinpoint that inflection point. And the inflection point is kind of important. It's major changes going on. Because when we're changing concavity, we're going from, let's see if I get this right, we're decreasing maybe at an increasing rate, and then we change to decreasing at a decreasing rate. So when we change, that inflection point tells us maybe we're a business or something, we're losing money really quick, but if we know that we've got an inflection point coming in, the losses are going to slow down, and we'll make it through. That's what we're hoping, okay? And hopefully our math will be able to predict that, and so we stay in business. If our predictions say, no, we're just losing money and it's just going to tank completely, we don't have an inflection point, we're going to say, okay, bankruptcy right now, and we still have something to get out with, right? So this is the idea with math, is using math to predict what our future might look like, okay? That's what the derivative helps us with. And that's pretty much it. You're ready to start into the assignment. It's 8 problems, did I say? Yeah, 8 questions. They'll give you a function. They'll give you practice. So this will also give you practice with taking derivatives, which help get you ready for that mastery test. And find where it's increasing, decreasing, max, min, concave up, concave down, inflection points. And then just work at looking at all the graphs.